So now we can use links, which is helpful for a lot of programs. It allows us to sort of keep the names the same, operate within a single subdirectory for our program, but still be able to access different files. And this helps to not duplicate resources across the system. We have two different names or two different paths, but we only have a single file now, rather than having to duplicate this file between these two directories. And then obviously, if we have duplicates, that means we have to handle things like what do I do when I update one of those? I have to try to replicate the changes, and that usually falls on the user to handle that rather than the OS. So linking makes it a little nicer for the user in that they don't have to worry about trying to handle updates to two different files and manage storage for two different files, all of that sort of stuff. So we talked about these a little bit before, that links are pointers to another file or subdirectory. And a hard link is a replica of the original directory entry for a file or subdirectory. So that means that we sort of have a physical copy of the object sort of header. Like, so the file information is duplicated. And we still have a link to this sort of node here, this circle that represents our actual storage. But we have a complete copy of the stuff that links to that storage. So the file name, the location, all of that sort of stuff gets duplicated. On the other hand, we have soft links, which are references to the path of the original file or subdirectory. So these are not full copies of that information. These are just sort of a path name that we associate with a new name. So it's a more simple link. It's just literally a new name for the same path. It is still a link to that file, but basically what it does is, if spell count is a soft link, we would have the reference that spell count actually links to dict count. And every time we access spell count, we would sort of go back through that path, get to count here, and from there we would be able to find the information about the physical storage of the count file. Whereas if this is a hard link, then spell count and dict count are identical. We can access the storage from both of those locations. We can get to this file without going backwards to the actual hard links. So hard links allow us to get directly to the storage. Soft links mean we have to go find the hard link, and then we can get to the storage. So any questions? Do we have any questions of that so far? Okay. So then let's talk about these two questions here. So this is a little more of an opinion question, or both of these are a little more of opinion questions, but I do want you to sort of discuss them together. So first off, how do we handle deletion of files that have symbolic links to them? And how do we handle deletion of files that have hard links to them? So go ahead and break out into your groups and chat about this for a minute. I'll come around to see what you think. Okay, I think those were mostly good answers. So I think there's a little confusion about sort of what the difference between these two is still. So um, yeah, so I think like the main thing is that the hard link is the actual sort of storage or has the storage information for that file. So like a symbolic link is just a path to a hard copy of the file. So we can sort of just leave those around if we delete a file that has a symbolic link, because then when we go try to actually find the hard copy, we're going to see that that was deleted, and we can probably just throw an error and sort of say like, hey, you tried to access something that no longer exists. It doesn't exist anymore. Sorry, we can't find it. Please try again. So we can just leave symbolic links to deleted files and handle it later. For copies with hard links have the storage or physical storage, or have a copy of the physical storage information for this file. So essentially what this means is that we either can't delete a hard linked file, like we can't delete the underlying storage because we have to assume that someone else has that copy, or we need to delete all of the hard links at once. So we have a couple options, but basically we need to make sure that we don't end up deleting the storage and then leaving a pointer into what is deleted storage, because once we delete that storage, it's possible that the OS reuses it for another file. And so we have this sort of situation. It's the same as having like a dangling pointer in C, essentially, where we now have a pointer into the storage that has been reallocated to some other pointer. And so now we have two files that are not supposed to be used for the same thing, but they're pointing to the same space in physical memory. So we have to make sure that when we delete hard links, we don't delete the underlying files. Don't delete the underlying files unless all copies are being deleted or are already gone. So we need to actually make sure that all of our hard copies are gone. And we'll talk about this a little bit more, how this works in a second here. So this is not too bad in an acyclic graph. Because of the fact that we don't have cycles, we can sort of, check pretty quickly to see from the root if we have any other paths that lead to the same file that we're trying to delete. Because we have this sort of tree structure. It's not quite a tree, but since it is a graph here, but since it's acyclic, we know that once we visited every node in the graph, then we have visited every possible file. If we don't find any copies of the same file, we can safely delete this underlying storage. So I just want to talk about this a little bit more, and I'm going to share a presentation here with you through Discord, through Hangouts. I'll post it there as well, just in case. I just want to talk a little bit about this in the general graph case. So the sort of next level up of file systems is a general graph directory that allows cycles in the links. So here we could only sort of point downward in an acyclic graph directory. In a general graph directory, we can have links that go upwards in the file system. So we can have like a directory here, D4, that sort of links back up to D2. And so we want to, in this case, this allows a little more flexibility for the programmer, right? Now I can, if I want to link a directory to some, directory higher up in the system, let's say that, I want to be able to get to user lib from my program. I want to use some system libraries. I want to link against those. And so I want to be able to get them quickly. And I want to make a folder in my directory that is to user lib on Linux. Seems like a pretty reasonable thing, or possibly also that I want to have, a proc file system reference that gets me back to the root directory from my directory, so I don't have to know like how many nesting levels I'm in. I can just get back based on this link. So there are a lot of reasons that you would want to sort of link upwards just for sort of the sake of ease of programming, ease of finding things in your file system. But what this means is now I have multiple paths. So I have /d2/f3 is a file getting to f3. I have /d2/d4/f3, which is also a reference to the same file f3. And then if we look at like, I have, these files that are linked together. So let's say these two are equal, right? They're the same file. I could have /d1/f1 is equal to /d2/f2 because these are two file names for the same file. So keep in mind the nodes here, these circles are the actual files that we're storing in storage. So if we follow /d1f1, that gets us to this file. /d2f2 gets us to the same file. And that would be equivalent to /d2/d4. And d4 is just another name for d2. /f2 is the same thing there. So we have a number of ways to access the same files in the case that we have cycles in our graph. We still have a number of ways to access the same files if we have links in general, but this sort of complicates the process because now we can go through an extra directory d4 that links us back up to d2, and then we have f2. So in this case, deleting files becomes a little bit more complicated. So let's say that I try to delete this file here. I want to delete f1. Now I have to figure out, do I have any links to f1 left in the system? So I can do that. I can delete f1. It's pretty clear from the graph that I still do have that link, but we need some programmatic way of doing this. So essentially what I have to do is, start from the root directory and see, can I still get to this actual storage node, this file stored in physical storage? So what I do is I, go from root, can check D2, basically go follow all the links from each of these things, going down here and then checking both of the children to see if they have any link to it. Basically just highlighting each of these as we go through the system. The problem then is that I'm eventually going to get to, D4, and sorry, I used the wrong color there. Eventually I'm going to get to D4, and that loops up to D2. So if I'm not smart about this, I end up in sort of an infinite loop of, scanning D4's children, scanning D2's children, scanning D4's children, scanning D2's children, and never exiting that loop. So we need to be careful about this to basically be able to figure out whether or not this node still has any links to the real file system or not, or if it's safe to delete that storage. So I'm going to go ahead and reconstruct that so that those examples are still there for later. So one of the options that the book talks about is to use what's called reference counting. And you may have heard of reference counting in context from other courses. It's often used as sort of a memory management storage technique to make sure that we don't have, when we want to delete something safely, knowing that there are no more references to it. So in this case, if we look at F1, or if we look at the file here, essentially what a reference count does is just annotates how many edges are incoming to that storage. So it's just a counter of how many references or how many pointers there are to this thing. And again, this gets used in context of like memory management in C++, as well. If you look at like the shared PTR class in C++, this is a reference counted pointer. So you can use this in your programming if you don't want to have to delete something manually. You can use a shared pointer, and that will allow you to basically create an object use that object, and then eventually have it be deleted whenever there are no remaining shared pointers to that object. So this is roughly the same idea as this thing that comes up in regular programming. Here we just basically have, when we make a file, we increment its reference count by 1. If I were to add another link to this, like if I decided to, add a file in E3 that linked to the same thing, right here. If I added another link to this, we would update its reference count to 3. So basically, every time we add a link, this would need to be like F4 maybe. Every time we add a link to a physical storage node, so one of these circles, we increment the reference count by 1. If I delete that link, I no longer have that file, we decrement the reference count. So every time we add a link, we increment. Every time we remove a link, we decrement. So not too challenging, hopefully. So again, if we want to know if we can delete this file, this actual physical storage or not, we can use reference counting in a lot of cases to figure out if that's okay. So let's say we remove F1. So we're getting rid of F1. That deletes that file, or that copy, that hard link to this storage. And now we only have a single pointer to that file. So we have a reference count of 1. So when I delete F2, if I see that I have a reference count of 1, I know that that's the only remaining copy of this. And I sort of illustrate that basically, like, if we have F2, that's going to decrement the reference. If we delete F2, that gets the reference count to 0. And then it's safe to remove this because we no longer have any links to this physical storage within our system. So can anyone see a possible problem here with the way this works?
So does it have to do with the cycle?
That's a good thought. So what could go wrong with the cycle?
You get stuck.
You get stuck, yeah. So great idea there. So let's see what happens if we let's say we delete, we have this set up here, so we still have 2 links here. And let me go back to the original graph here, actually. So we have.
Would it be that it gets stuck, or would it look like there's infinite references to that file object?
So it should just still be a single reference, because it's just the pointers itself. So it's not sort of going through the entire thing. It's just when we add a direct reference to it, it updates the count. But let's say here then, let's delete this link. I delete that link. Now I have a reference count of 1. But let's say I somehow unlink this from the system. So now, and this is sort of going back to, like, can I delete a directory without deleting all the files inside of it? So this is a bit of an issue here. So now, because of the fact that I have this cycle, this directory has a reference to itself. These directories all have references to them. This file, the storage, has a reference to a file that is not gone. This file, this hard link, has a reference to this storage. So I have this sort of whole subgraph that, because there is a cycle, I can't really delete the storage for any of it. And so this is a small problem with references, or with reference counting, that is common to all reference counting problems. So if you use shared pointers, this is a tricky thing, that, like, a linked list with shared pointers that has, or like a circular linked list, will not delete itself, because there is always a reference to each thing because it has a circle or has a cycle, that means that we can't actually delete it. So if we have this setup where we sort of remove the links, we will be unable to delete this subgraph here, and we won't be able to reclaim the storage for all of that. So we want a solution as well that can sort of handle this. This is probably okay, but then we sort of have to have that condition where we can't delete a directory that isn't already empty, especially in this case. Okay. So this is just, I think, generally a good thing to keep in mind. You will run into this in other cases with programming where like reference counting can be a very nice way to sort of remove things from the system automatically, but you run into this issue that cycles will cause problems. And so you have to essentially break the cycle yourself. So like here, the programmer would basically have to make sure that there is no loop back on this. And if we delete this loop back to D2, then now D2 doesn't have any references, we can delete it. Now these three don't have any references, so we can delete them, and then eventually we can delete the physical storage. So if we don't have the cycle sort of going back to D2, all of the reference counts will fall to 0, or they'll sort of chain to 0, and then we can delete everything. So the other solution to this is to do what we call garbage collection. So with garbage collection, and I did have this as an actual presentation. With garbage collection, what we do is basically start from the root node of the file system and traverse to all of the children. And then anything that we have been able to find with garbage collection, we can keep, and anything that we weren't able to find, we get rid of. So we have to basically know like where the root of this system is. Essentially, that's just here, right? In a file system, it's easy to find the roots. In like a programming language, finding the roots of memory is a little bit harder. But in a file system, we know that the root is the root directory. So we start at the root. We basically color in that node to say that I was able to reach that node. And so then once I'm at that node, I traverse to its children. So I visit D1 and D2 because those are the children of root node. And then we basically push those onto a stack so that we visit their children. So I visit the children of D1, and then I visit the children of D2. I push all of these onto a stack, and I'm going to visit their children in order. And eventually, we get to the actual physical storage for each of these nodes. So in the case that we have the complete graph, we basically go through from the root node to the child nodes, and we find that we can, in fact, visit every node in this graph, and that there's nothing to delete here. If we have deleted these edges, like we just talked about, then we do the same basic thing where we visit the root node, we visit its children, we visit that node's children, and then we get to this file. So here we can identify that we should in fact delete that entire right subgraph of this, because we know that we don't actually have any links remaining to that subgraph because of the fact that we can't reach it from the root node. So this is the garbage collection approach to sort of collecting all of this. And here I can safely delete that directory without making sure that it's empty. Because eventually the system will come along and collect all of this garbage that is no longer reachable from the main file system. So this is a sort of more complicated but more powerful technique for cleaning up the storage. It allows you to sort of provide that extra flexibility to the user if they want to delete a non-empty directory, but still be able to manage the fact that we do have storage left over that we need to eventually clean up. Often the way systems do this is that essentially what would happen here is that you would remove directories, keep that fast. So this would just be like an unlink from the root directory. And then when we get to the point that we do need more storage, then the OS would sort of go through and find all of the empty storage, like the stuff that it can clean up and garbage collect and reuse. rather than doing it immediately. So this tends to be a lazy process where we sort of, go along about our business, and then eventually when we run out of space, we trigger garbage collection, and that causes this space to be freed up. So what questions do you have on reference counting and or garbage collection? Okay. So that's it. That was sort of covering this question here. So what file system functionality becomes more difficult to implement is deletion. Need either reference counting or garbage collection to handle gracefully. It's just a lot more difficult because we have to manage the fact that there are these cycles, whereas in a tree directory and an acyclic graph, we can easily use reference counting and we don't end up having a problem here. Okay, so those are all of the files. Sorry, was that?
Can you clarify that question? Because it seems like it's asking, or it's saying that for non-cyclic. Oh no, wait, I misread that. Acyclic. Okay.
Okay.
Sorry.
Yeah. So that's directory structures. Not too difficult, hopefully. We do allow links, so we're either looking at, we are looking at a general graph directory in like a Linux system, because we do allow cycles back to older, or folders up higher in the hierarchy. So we want to think about the directory system as a general graph directory with all of these sort of complications, that we do have to handle this sort of cyclic nature of the graph and deal with that. So let's just sort of dive in a little bit to file and directory protection, and then we'll finish up with that on Wednesday. I have been slacking, by the way, on the reading quizzes. I apologize for that. We might have a very short one for Wednesday to pick up, but I would recommend, if you haven't already, reviewing section 13.3 sort of on your own time to make sure that you're good with that material that we just covered. But we'll have a short one for protection for Wednesday, and then continuing on Friday. So file directory protection is the general idea that we want to protect the file system from unauthorized access to files and directories. So because of the fact that in a general system, we don't have, like, if we have a two-level directory system where we just have users and their files, it's not too hard to protect the file system, right? We just basically say, are you this user? Okay, you can do whatever you want to this file. In a general system, general graph system, we have to make sure that when we have these non-user specific folders, that only the users or groups or people that are supposed to be able to access this file are able to access that file. There are a number of operations that can be controlled. So reading from a file, writing from a file, writing to a file, executing a file, appending to a file, deleting a file, listing the attributes of a file, changing the attributes of a file, and then other operations like moving a file, for example. So moving a file is generally reading, deleting, and then writing a new file. So we want to be able to control the operations that a user can perform on these files. Generally speaking, the OS will sort of control some number of these, and then will classify certain operations as a use of this type. So like deleting a file might be the same as writing a file. Appending to a file is probably the same as writing a file. Listing attributes and changing attributes are sort of based on a user in Linux, like who the user is that owns that file. So some of these might be combined. They might not be specifically like I have a permission to do this as this particular user. It's sort of assumed based on the rest of the permissions that we have for that file. So the most common approach to this is using an access control list. So you will hear the term ACL in security and protection conversations. This is an access control list that basically just specifies users and operations. So, you know, we might have a file, file.txt, and we would have a list for file.txt that says, like, you know, Professor Delosier is allowed to read, write, execute, change attributes, list attributes, delete, something like that. And we might have like RuPom's on top right now. So RuPom is allowed to read and write the file, list attributes. Tyler's next. Tyler's allowed to write the file, maybe just read the file. Ethan's allowed to list attributes and delete the file for some reason. So this is an ACL. Just an example. So it essentially just has a user and all of the things that the user is allowed to do. So when we access a file, we open the ACL for that file as the OS. We check to see, does this user have this permission? If the user has that permission, we allow them to continue. If the user does not have that permission, we prevent that access as part of the protection scheme. So not too difficult, just what the ACL would do. So the problem with a sort of generic ACL is that it is a variable structure. So for every file in the system, we have to have this sort of, you know, extra file associated with it that has any number of users, any number of permissions that might be associated with those users, and it's not necessarily the most compact version of this that we can have, because of the fact that we sort of list these specifically for every user. So this is not too bad if we have 4 users that are accessing a file, but if we have, you know, 100 user systems, or like, for example, thinking of like properties for files that are underlying the MIDS system. So like MIDS has, you know, thousands of users. If we had to have an access control list for every user in the system, for every file in that system, you know, that might be like your AC advisor, you know, the department chair, you, and then everyone else has to be listed as having no access to that file. So we can end up basically like this file gets very large. These ACLs get very large and complicated very quickly. So modern operating systems use a condensed version of an ACL that sort of condenses these permissions into an owner, group, and others. So others can sometimes be called like everyone as well. So the owner of the file is the user that created the file. The group is a set of users who are sharing the file and need similar access. So this is common to, like, if you think again of, I'm gonna use MIDS as the example here, and I pull it up that we can look at this. So if we look at MIDS, you can see that like we have AC Center, Commandant Staff, Department Chair, Faculty, Logistics, you know, Mid Personnel Office, Midshipman, Phys Ed, ProDev, Registrar, right? And so this is the general idea of having these groups, so that we can assign and say like, okay, you are all midshipmen, so you have permissions to do these things, right, to files in the mid system. Faculty members have permission to do all of these things. Department chair has more permissions to be able to do additional things. And so that's the general idea of groups, is basically that we have these sets of people that have similar access to files in this system. It allows us to basically not specify permissions for every particular user, right? I might be able to then say that, you know, Rupam, Tyler, and Ethan are all midshipmen, and so they all have the same permissions as part of a group for that file. And then other is all other users, everyone. So if you are not the owner and you are not part of the group for a file, you fall into the other category. And that means that you have usually a reduced set of permissions. So generally the way that, you know, files are protected is that the owner has the most permissions, the group will have a more limited set of permissions, and then others will have the least set of permissions for a file. So I think it's probably best to stop here for the day, because we're going to end up diving into how these are actually represented and how they look on a Linux system. So I think it's best to get there on Wednesday. So if we have any questions, I'm happy to answer them till the end of class time or after. Otherwise, I will send out your exam feedback after class, and feel free to let me know if you have any issues. Otherwise, I will see you on Wednesday.
Professor?
Yeah.
Are we gonna, is it just reading quizzes this week, or will there be a homework as well?
It should just be, we do need a homework for 9, I believe, still. So there will be a homework for 9 and 10 at some point, but it won't be due by the end of the week. So for due this week, we'll just be reading quizzes.
All right, thank you.